I should tell my students 4:30. 3:30 is the time to...
Okay, let's get started. I don't think there's any room for anyone else. Welcome to the last free robotics seminar. I would be charging admission after today. So we have to do something. It's my pleasure to introduce Pieter Abbeel. Peter's a professor coming to us from Berkeley. He did his graduate work at Stanford. He's one of the rising stars in robotics and machine learning. Past the rising part, he's just a star now. And I will let him talk about some of the cool stuff he's been doing, and then I'll try to not step on too many people on my way back.
Thanks, Drew, for hosting me, and thanks everybody for coming out. It's a great pleasure to be here at the Robotics Institute. I want to tell you a little bit about what I've been working on from the end of my PhD through now. And I want to start out with saying what has kind of been the main inspiration of my recent work. So this video here, many of you might have seen this video before, but this video came out in actually the unpublished version came out around 2006, late 2006. And I was at Stanford at the time, PhD student there working in Andrew Ng's lab. And these were two students working in Ken Salisbury's lab, and they built this robot. They sent a video, and I was watching the video that they sent to everybody in the AI lab there, and we're like, wow, it looks like robots can do everything now. It's really cool. So essentially, this robot is doing the kinds of chores that a lot of us hope and many other people hope robots could do. But the catch, of course, here is that somebody is tele-operating the robot. For people working on the software/algorithm side, of course, this is good news. This means that if you could just make the algorithms better and the software better, then maybe we could have the kind of robot that would do all the chores for us. So a little later, Keenan and Eric, who were the two lead students in that project, went to out the private market, so to say, and started a company called Willow Garage. Not technically started it, but it existed, but they kind of became the main project. Leads at Willow Garage, they started this new project on building a more robust version of the PR1, which you saw in the video. That robot came out in 2009 for $400,000. Then this year, Baxter came out for $30,000. So maybe we can be hopeful that if we wait another 4 years, through a lot of hard work for sure, maybe something will show up that's only $2,000 in 2017. So this really motivates me to look at manipulation problems and see if we can come up with algorithms and software that allow us to do more reliable manipulation than we can do right now. If you look at robots right now, mostly they're in manufacturing. They're doing amazing things there. I would say the big difference is in manufacturing, you can engineer the environment around the robot. In a household and office, you cannot. And so to take that to the extreme, I would say, is to look at objects that even when you see the same object again, it's not in the same shape, the same motions would not succeed. So objects that deform. And so the task I've been interested in taking on as challenge tasks in my lab are how to get a robot to do laundry and how to get a robot to suture, medical suturing. And when I got to Berkeley, we started working on this. This is back in 2008, we started working on this. And then by 2010, this is the result we got. This is an early PR2. And what's going on here is the robot is using its cameras to map out the geometry of the towel, carefully finding the corner, then finding a neighboring corner. Once it's found the neighboring corner, it's checking if there's any twist at the top. Once it's found the way to untwist if necessary, it goes to the other table and then folds and stacks it away. This video is highly sped up, by the way, about a factor 200. Where about is a very precise number. It's really exactly 200. We have sped up the robot since. It can now do it in 2 minutes instead of 20 minutes. But overall, I think the key takeaway here was that it could do it quite reliably. We had the robot do this 50 times in a row without failure. Each execution was 20 to 25 minutes. It was a pretty long, thorough test. And if you look at what we did, I would say we had many contributions related to this work. Some in perception, some in perception action loop, some in hierarchical motion planning, and some in specifics of how do you do planning for folding things. But overall, I would say it was a lot of hard work, and it took 2 to 2.5 years to get a robot to fold towels. That's not a good state to be at if you want to teach a robot a new task. You're going to be busy for a real long time. If it's just towels takes you 2 years of 2 or 3 students who really dedicate their time to that, that's too long. And it's another way to look at what we did is we looked at a problem that was hard, worked hard to get it to work, but also realized that a lot of things are missing and we need to maybe take a little step back again and not hope to get things to work right away, but look at some more abstract problems and try to make progress on those. And we made a list of problems that we thought we should make progress on. And once we've made progress on all of those, maybe we'll go back to do a more complete laundry task. And so there's a list here. I can't talk about all of them here, obviously, but we have worked on all of them. I'll try to highlight the first 4 bullet points. We've also done some work on the later ones. In particular, the tracking we spent a lot of time on to reliably track deformable objects. And recently, some collaborative work with Stuart Russell on how to tie classical AI planning to motion planning. But those are for a separate conversation. So let's look at robot learning from demonstrations first. So my motivation is that for going back to learning from demonstrations, that during my PhD, I did work on learning from demonstrations. And we called it apprenticeship learning, the idea being the robot watches a human do something, learns from that, and then learns more on its own to fine-tune its skills. But we didn't do it for manipulation. We did it for something else. We looked at a helicopter. So what's the problem there? You have a dynamical system that's unstable, meaning you continuously have to adjust the controls to just keep it in the air. It's nonlinear, meaning linear control techniques don't directly apply. The dynamics is not just nonlinear, it's complicated, especially because of the airflow around the helicopter being very difficult to model. And then you might not have perfect state estimation. So you have some approximate estimates of the state. In general, what you might think about as just hovering a helicopter is actually a really hard problem. You should try it someday if you have a lot of time. It's hard to get that to work. And there's been a lot of papers written on this, considering different ways of getting that to work, including some work done at CMU. Drew Bagnall, Jeff Snyder worked on this, getting hovers to reliably hover. If you look at these papers, I would say one common thread is that the control techniques actually differ quite a bit between the papers. Some of them are learning-based, some of them are hand-tuned, some of them use linearization-based control techniques, some of them use nonlinear control. And so I would say a big part of the challenge here is that somehow everybody figured out how to get a helicopter to work, to hover reliably in a stationary regime. And then how do you go beyond the stationary regime is what we wanted to look at. So how you do something, let's say, like flipping a helicopter. We looked at all these papers. We took what we thought was the most reasonable way to proceed. And we got the helicopter to flip. And then we lost control. So the engine died on us, and that's what happened. Why was this hard? Why didn't this succeed? Looking at it in hindsight, what was hard was to specify a trajectory for the helicopter to follow. So there's a lot of good control techniques out there to stay on target if you have a good target. But we didn't know how to specify a good target. So we specified a bad target. We specified a very idealistic flip. And that was not possible. And so it started deviating more and more. Error accumulated. The controller was not designed for being that far away from its target trajectory. And so things went really bad. So what we started looking at is, well, how do we design a trajectory that we can actually fly? By hand wasn't succeeding. So we said, our pilot knows how to fly. Collect data from our pilot. Use that as our target. But then the pilot wasn't really flying perfectly either. So we said, we want to fly a trajectory that's cleaner than a single demonstration, get multiple demonstrations, and somehow extract out a cleaned up version. So here's an example of what that could look like. You take your pilot out. He flies multiple times the same sequence of maneuvers. And you track the helicopter during this process. And here's a replay of about 6 times the same air show being executed by our pilot. You see they're all air shows are going through a loop here, not at the same time, not exactly the same orientation, but you can see the similarity. You can see that there is something common there that in principle could be better than just each individual one on its own. So how to extract a cleaner version from all these demonstrations? There's a lot of work on cleaning up time series. So what we looked at was HMM-like models. So we think of the state sequence that we don't know for the hidden intended trajectory to be sequence of helicopter states that we don't know, to be connected from time to time through the helicopter dynamics model. Then the demos we get are observations of this unobserved intended trajectory. A little tricky part there is that the demonstrations might have a variable duration. It might not be timed the same way, so we need to find a solution for that. So here's what we do. We somehow fill something in the top trajectory that we don't know yet, just to initialize the process. This could be one of the demonstrations, could be some estimate of what is the right thing. Then we use something called dynamic time warping, which comes from the biological sequence alignment literature and also reinvented in the speech recognition literature. It's a way to align pairs of time series. Turns out it's computationally expensive to align many time series, but for pairs it's quite tractable. So you align each demonstration, which in practice would be 5 to 10 demonstrations, to the hidden trajectory. The hidden trajectory then now is connected to actual observations that are lined up with it. At that point, you can just run a Kalman filter smoother forward-backward pass, get out an estimate of the hidden trajectory. Now you have a better estimate of it. You can disconnect the alignment, realign pairwise, rerun the Kalman filter smoother, and this way you get out a cleaned out version of your trajectory. Here's what it looks like. The white helicopter here is the intent that we inferred for our pilot. The colored trajectories are still the same as before, but now retimed through the dynamic time warping. The trajectory we get out is actually cleaner than what we had from any of the original trajectories, partially because our pilot is not flying perfectly, partially because we don't track the helicopter perfectly. So often when you just look at these trajectories that were recorded, you'll see weird kinks and so forth, because just our sensors aren't that great, and we get noisy trajectories out. But this way we get a denoised clean version. Now we have a target trajectory. How does the whole system work? We have a helicopter, a remotely controlled helicopter. On board, there's inertial sensing. There are cameras on the ground looking at the helicopter. You could use a GPS for position sensing, but the reason we use cameras is because GPS doesn't work well when you don't face the satellite. So once you go upside down, your GPS will be looking in the wrong direction. Also, if you accelerate really fast, GPS tends to lose lock. We fuse in an extended Kalman filter the inertial information with the camera information, get out a pretty reliable state estimate, feed that into a model predictive controller. At the time, what we used was a receding horizon differential dynamic programming controller, which essentially means you start at the beginning, have a current policy, execute it, execute it in simulation, linearize around that trajectory, then run LQR backups from the end to the beginning to find a feedback controller, then execute that feedback controller, relinearize around the trajectory you found, and keep repeating this till you converge to a local optimum in terms of as closely as possible following your target trajectory with a feedback controller. We actually run this online, so rather than just running this ahead of time and re-executing the linear sequence of the sequence of linear controllers, we recompute this with a 2-second horizon. So after every 1/20th of a second, we recompute with 2 seconds look ahead what the optimal controller is. We send then out the controls to the helicopter, which then has servos on board that will execute those controls, and the loop gets closed. So overall, what we have is collect some standard data from your pilot doing frequency sweeps and or step inputs to your helicopter. Then your pilot will demonstrate the air show about 10 times. You learn a target trajectory as I described. Now a side effect of learning the target trajectory is that you get these nicely aligned time series. And that allows you to learn dynamics models that are specific to where you are in your maneuver, which allows you to learn very accurate models for pretty aggressive maneuvers. Once you have these accurate models and you have your target, you can run the control procedure offline. You would then fly with the receding horizon controller. Usually you would get about maybe 10, 20 seconds into your air show. At that point, your pilot would take back control. You would use the data from the first 10, 20 seconds, feed that into your data set you use to learn your dynamics model, improve your dynamics model thanks to that. Iterate this process. Next time you'd probably get 30 or 40 seconds into your air show, and keep repeating this process until you get the full 1 or 2 minutes of your air show done. Usually this takes about 10 to 20 iterations till you're all the way through and have converged onto a really good dynamics model. The reason the data here is useful and helps a lot is that the pilot data isn't perfect. They're not always flying the same thing, but once you start getting computer-flown data, it's very consistent, and you get data exactly around the trajectory where you want it. So in less than an hour, you can learn to fly new maneuvers quite reliably. Here's an example of the result we got. So this is all fully autonomous. Hover. Then we do forward flight, followed by a split S, which is a way of changing direction. Snap roll, stall turn, another way of changing direction without burning your kinetic energy to friction. Loop. If you are good at doing loops, you show off at the top that you're good at it. You do a little pirouette. Stall turns, you can just as well come out tail first. Fast backward flying circles is what they call hurricanes. We've flown this helicopter up to 45 miles an hour. Inverted hover. Knife edge fall. And then this is where I would argue is where we do the hardest maneuvers. Why? These are the hardest maneuvers because we're maneuvering in the airflow that was just generating. So there's a very unpredictable airflow, hard to model airflow around the helicopter through which we're controlling it. The least efficient way of keeping your helicopter in the air. And this is actually the most efficient way of flying. The reason being that when you pull air in and then push it down, it's faster below the helicopter than above. And the drag you generate on the helicopter body is hence lower. You generate less drag on the helicopter body if you keep it above the blades than if it's hanging below your blades. So maybe in the future you'll fly helicopters that way if it's mechanically feasible. Okay, so what we looked at is an apprenticeship learning approach where we leverage expert demonstrations to then learn a trajectory and a dynamics model around the trajectory and solve essentially a control problem that people hadn't been able to solve before. And I gave this presentation at the University of Washington in 2008. And Blake Hannaford was in the audience. He works on surgical robotics. And he said, well, that's all great, but I think I have a better problem for you. Surgeon is your pilot. The Da Vinci tools inside the patient are your helicopter. At this point in time, about 400,000 surgeries are done each year with this system. So in principle, you have 400,000 demonstrations. Why not learn from that and learn to do surgeries? Right. It's a very different problem, right? And I would say what's fundamentally different about it is that with a helicopter, we're working in open airspace in what we did. And so we have to adapt, but we have to adapt to wind gusts. And the way you adapt is by kind of canceling things out. You undo perturbations. Whereas here, you actually want to adapt to the situation and do something different based on the situation that you're encountering. So you somehow need to learn to adapt what you're doing to what the situation is, as opposed to reject perturbations. So I said, let's first look at a very specific problem, which is knot tying. It's a frequently reoccurring task. It's a little tedious, so why not just automate that first? So the way they do that is they have suture, they wrap one end around the other, they grab it with one instrument, wrap it around the other instrument, then pull through the loop and get a knot. We started working on this, and the first thing we said is, well, it is different, it's suture now, but how about we just do the same thing? We just have an expert demonstrate knot ties. record the robot motions, and let's ignore that maybe we need feedback. Let's just control the robots around the trajectory that's learned from demonstrations and see how well it can tie knots. This video featured a current CMU PhD student, Shervin Javdani, over here, with some explicit language. The lesson learned here is that Shervin and Stephen were not expecting this to succeed necessarily. They were quite happy it succeeded. And if we looked at the success rate, indeed, the success rate ended up being about 50%. So if Shervin and Stephen, who really wanted this to succeed all the time, were careful about setting everything up really nicely, we'd end up with about a 50% success rate. Why is that? Because you need to adapt to the suture. You can't just go through the same robot motions and assume that things will succeed. So canonically, what we're looking at here is a problem that's a little different than just learning a trajectory. We're trying to learn a trajectory, or a way of adapting trajectories to situations. So let's say you get a demonstration for the rope laid out as shown in the top here, how to now adapt those motions for it to work for the rope shown at the bottom. There's actually been a lot of work on learning from demonstrations in robotic manipulation. I'm listing some work here. So the work by Aude-Biard and Sylvain Calineau looks at building Gaussian mixture models and then learning trajectories as Gaussian mixture models effectively, where once you see some variables of the trajectory, you can predict the other variables, which is the next time in the trajectory. Stefan Schall and his students have worked on dynamic motion primitives, which is for more dynamic actions. Then Maya Sakmak and Andrea Tomas and their collaborators have looked at not so much changing the representation of how you learn, but assuming somebody build a representation to do learning from demonstrations, how do you build a layer on top so that you get human-robot interaction? The robot can start asking questions. How about the demonstration for this situation? How about if I went this way about it? Would it still succeed, and so forth? To learn faster than just passively observing. And then Jan Peters and his collaborators have looked at reinforcement learning approaches where you say we're going to seed it by demonstrations. So quite similar to the helicopter approach, where you have demonstrations, start from them, and iteratively get better through self-trials. Now, I would say what's missing for us, if we're looking at deformable objects, is the representation they use underneath are coordinate-based representations. And it's hard to define a coordinate system on a rope or on a piece of cloth that's right for what you want to do here. Instead, it'd be nice if you could just work in terms of a point cloud. You say, this is the geometry, the overall geometry of the thing we're looking at right now. Can we learn directly from that? You could, of course, argue, you could always put coordinate frames on every point in the point cloud. Isn't that the same thing? And I would say the difference is that you'd end up with a lot of coordinate frames. And you would end up needing a lot of demonstrations to apply these techniques if you had that many coordinate frames to deal with. So you would be having a very high-dimensional learning problem. You definitely could not learn from 1 or 2 demonstrations if you applied those approaches with coordinate frames on every point in the point cloud. So let's take a look at how we can directly work with a point cloud. Let's say your train situation looks like this. Just 4 points in the point cloud. It could be any number of points. And your target trajectory, in this case, looks like that, adapted to the points. Now you get a new situation. The points have moved. And the question is, what's the right target trajectory now? I think most of us have an idea of what it should be. You have some idea of, this is what I'm going to draw here. Should be about right. The question is, of course, how to build a system that can infer that new trajectory automatically. What we start looking at is non-rigid registration. There's a vast literature, especially in the medical imaging field, about how to register images onto each other. And so, for example, for this point cloud, you could use non-rigid registration to register the points onto each other. Once you have done that, kind of novelty in our scheme here is that we don't just register but then use the registration in a way that hasn't been done before, which is we think of it as samples of a function that maps from R2 to R2 or R3 to R3 in general. Machine learn the entire function, and then use that learned function to transfer over the trajectory. So the idea here is really to use existing non-rigid registration techniques, but then extrapolate them to apply them to the trajectory that was demonstrated to get a trajectory for the new situation. The question, of course, is how do you extrapolate this registration? So you're trying to find a function that satisfies these constraints. Your train points get mapped onto the correct test points, where f is some function you're trying to find. There's infinitely many functions that will satisfy this. You want to find one that's hopefully reasonable. One choice you could make is the following. So what is this saying? It's saying of all functions that map from R3 to R3, pick that function that minimizes this integral here. This integral is the sum of the squares of the second derivatives of that function. What does that mean? That means that translations, rotations, and scaling are free. So if there's a way to just translate, rotate, and scale the train scene onto the test scene, you'll use that. It also turns out that you can solve that problem very efficiently. Even though it's an optimization over all functions, which is a big space to optimize over, there are methods to solve this efficiently. In fact, this work has been done quite a few years ago. It's called a thin plate spline model. And it's been shown that the optimal solution to a problem of that type will be of this format here. Your function f of x will be a sum of basis functions that's centered around the points you're registering, plus an affine part. The kernels that define the basis functions are also known ahead of time and depend on the dimensionality of the space. And you know ahead of time the dimensionality of your space. You just fill in our case 3, and you'll get one of those kernel functions. Once you use that representation, which we know includes the optimal function, it just becomes pretty much a standard least squares problem to find the optimal solution. So let's take a look at how well this works. So here's a student, this case Jonathan, demonstrating in NotTie by moving PR2 around. So in this case, we'll be using just one demonstration, just that one demonstration. The top left, you can see how train and test, or demo and test, are quite different. There is some non-rigid morphing that has to happen to map them onto each other. Then the first trajectory segment gets predicted, gets executed, a new picture. A square knot. All right. So this worked quite well for the knot tying. In terms of quantitative evaluation, it works reliably if we lay out the rope and then perturb it randomly up to 2 inches, arbitrarily a few points along the rope, let's say 5 or 10 points along the rope, perturb their location by about 2 inches. It'll work quite reliably. Once the perturbations are more than that, often it doesn't generalize. So we would need more than one demonstration to go beyond that kind of range. There's a lot of extensions that are possible that we're currently looking at that I think will be important to generalize further than that. One of them is, it's true we're favoring affine transformations right now, but that might not be good enough. I mean, affine still allows for scaling, still allows for skewing. Maybe we want to favor just rigid transformations. So we need to change the objective that we use. we're not transforming the entire gripper. We're just predicting a trajectory for a coordinate frame attached to the gripper. Position and orientation, but still just a coordinate frame. Often in the manipulation, you want to really adapt to the specifics of the geometry, and you might want to incorporate the entire geometry of your gripper into what you're morphing here. Rotation-wise, rotating around the z-axis is much more favorable than rotating around any other axis in terms of maintaining invariances. None of these things are incorporated yet in what you saw. You can imagine doing something similar where you also generalize over the geometry of the tool. Not just morph the scene, but also morph the tool and make sure that the morph tool still fits in the scene. And then you can imagine start pairing this with the existing methods that use Gaussian mixture models or dynamic motion primitives, which are more discriminative, especially the Gaussian mixture models. But then that might have advantages in and of itself in terms of being more prediction oriented. Okay, so that's the learning from demonstrations. Let's now take a look at optimization-based motion planning. It's part of what we have to do in what you just saw. Once we try to generalize at the gripper level, not at the whole robot body level, because it's easier to generalize gripper motion than to generalize whole robot body motion. So we still have to make a motion plan for the entire body of the robot. So how do we do that? We start looking at that, and in more general, it's a problem in robotics to somehow plan paths from start to goal. And one of the things we've started to look at is optimization-based approaches, largely inspired by the work by Sid and Drew here. A paper on Chomp back in 2009 showed that you can do surprisingly well. Surprising at the time, maybe less surprising now. If you start your PhD after that, you might not be surprised. But at the time, it was very surprising that with optimization-based approaches, you could do quite well in motion planning. So a little bit on optimization here to give you a little bit of background of what's going on. The easy problems in optimization are convex problems, typically. That's a broad category of easier problems. You minimize some function f0 of x, which is convex, meaning bowl-shaped, unique optimum typically. So easy to find, you just descend. But you can also have constraints. fi of x smaller than 0, meaning that your function has to lie in some convex set if fix is convex. And then ax equal b, that's a linear equality constraint. Boyd and Vandenberg have a great book on this. There are many packages out there that can robustly solve this type of problem. A lot of problems, including motion planning, are not convex. So a very popular approach these days is to do something called sequential convex programming. One way to think of it is as follows. If a non-convex problem, you could say, well, too bad. You could do a gradient method. But gradient methods aren't necessarily all that great when you have not so great scalings between your different parameters. You can say, well, I'm going to use a second-order method, essentially use a second-order approximation locally, which will likely be better, and you might make faster progress. This is taking it one step beyond the second-order approximation. Say, I'm going to locally approximate my non-convex problem with a convex problem. So from gradient to Newton method to convex local approximations. That's kind of the progression that we're making here. The best book to read on, or maybe not best to read, but as a reference is the Nosedal and Wright book, chapter 18, if you want to find out more. So it's not our contribution. It's all written up. So now g0 of x is non-convex, gi of x non-convex, hj of x not a linear function. The way you solve this with sequential convex programming is as follows. You define a merit function, f mu of x. It still has the original objective, g0 of x. And then the constraints are gone, but are now present as additional terms in the objective. You have a coefficient mu times then the sum there is over all inequality constraints. You evaluate them at your current point x. And if it's positive, you keep the number. If it's negative, you set it to 0. So that term, gi of x plus, is 0 if the constraint is satisfied, is whatever it is positively if the constraint is not satisfied. So if you minimize that term, you'll drive it into the part of the space where the constraint is satisfied. Similarly, hj of x, absolute value of that will be 0 only when the constraint is satisfied and non-zero otherwise. You can show that if you do some local optimization scheme on this, and there is a local optimum that satisfies all the constraints, you will find that local optimum with a finite mu. So you don't need to make mu all the way to go to infinity. You'll keep increasing this, but at some point you'll have increased it enough. Why not make it really large from the beginning? Typically, the smaller mu, the better the problem is conditioned. So you start with a small mu and then crank up your mu. It'll get worse conditioned, but that's fine because you're already closer to your solution by that time. So we'll solve this problem with a small mu first and then crank mu up until all the constraints are satisfied or no progress is being made, meaning that you're stuck in a local optimum that doesn't allow you to satisfy all the constraints from there. What does it mean to locally approximate? To solve this problem, you locally approximate with a convex problem, which looks like this. You take a first-order approximation to the objective function. You take first-order approximations to your constraint functions, gi of x and hj of x, which are sitting inside these absolute value and positive part of the function. Then you have a thrust region constraint, meaning you don't want to move too far from your current point because your current point determines your linearizations. And so you don't want to be too far away from that because then you might step to a part of space where your linearization was not valid and it's then not meaningful. So this is how you solve these problems. Locally approximate, find the optimum. For that optimum, stick it into your merit function. If it's better than what you had before, you keep it. If not, you shrink your thrust region. Or a more sophisticated approach is you see how much you improved according to your convex approximation. You compare that to how much you improved according to your merit function. If that improvement is comparable, it means your convex approximation was good. You keep it. If not, you shrink your thrust box size. OK, now we're going to connect this to motion planning. So a lot of methods, especially before CHOM came about, most of the popular methods were sampling-based and graph search methods. The tendency of those is to slow down as the dimensionality of your problem goes up. Optimization-based methods don't tend to slow down as much as your dimensionality goes up. There are some very early optimization-based methods. Khatib did it for control, not planning, but control. Then they did some later work also for control. But then really kind of what kicked it off as an approach that people thought was viable for motion planning rather than control was the work here by Nathan Ratliff with Drew and Sid. And then many variants have come out since. So what does it look like? You optimize the trajectory. Let's say the robot joint angles over time. You don't want the joint angles to change too much from time t to t plus 1. There might be some other costs that you care about. Then subject to at time 0, you're in your start state. At time capital T, you're in the goal set. You satisfy joint limits. And for all robot parts and for all obstacles, you want no collision. That's the non-convex part. That's the hard part. And the solution method here will be the sequential convex optimization approach that I just mentioned. So how does that work? Well, there's a very efficient way to compute distances between two convex shapes. There's the GJK algorithm and the EP algorithm. If you combine them, one does it for in collision, one for not in collision. It computes a signed distance, meaning what is the minimal amount of distance two objects have to move to get into collision or to get out of collision. That's a number you can compute very efficiently. We can take that number, we call it the signed distance, and we make it a constraint. We say the signed distance has to be such that we're not in collision. So signed distance has to be bigger than 0 would be the constraint here. In the sequential convex optimization approach, we'll be linearizing that signed distance. What does that mean in terms of our variables? Signed distance is you have the normal direction between the two objects corresponding to the minimal motion to get into or out of collision. You have point B being the obstacle that doesn't depend on any variables, suppose of the obstacle. And then point A is a robot link, let's say. So it depends on the joint angles of the robot. You can linearize this using a Jacobian. You get an expression like this. And so now your linearized collision constraint looks like this. And this is something you can use in the inner loop of your sequential convex optimization approach. Effectively, what it looks like is that you're penalizing more and more the more your two objects are in collision. The outer loop that cranks up the mu penalty will crank up this penalty to become steeper and steeper. Now, one thing you want to avoid is that we're working in discrete time here. You don't want to jump through obstacles. So you want to make sure that from time t to t plus 1, you keep track of the volume that was swept out by your robot links and make sure that the entire volume is not in collision. Turns out that the GJK EP algorithms that we rely on to do collision checking can do this about equally as fast as just collision checking for one of them. It's just a factor 2 slower. An upside here is even though that's a factor 2 slower, overall you might be able to sample your trajectory more coarsely, so you might actually have a speed up thanks to that overall. Overall it can be faster because it tends to make for a better conditioned optimization problem. You're now really looking at the shape of your trajectory rather than at discrete points along your trajectory. And so overall the optimization tends to be better behaved, and overall it tends to be a gain in all regards to do the continuous time collision checking. Now one of the properties of the RTs and A*-like approach is that asymptotically, if you keep refining your discretization or you keep sampling, they are guaranteed to succeed. It might take a long time, too long for practical purposes sometimes, but they're guaranteed to succeed. These optimization-based approaches don't have such guarantee. So the way to evaluate them is doing something like building a benchmark. You set up a bunch of test cases that are realistic, of interest. In this case, robot around the bookshelf, robot in the living room environment, and give goals, start states, and see how often this approach succeeds, how long it takes. So we did that. We looked TrajOpt is what we call the algorithm we implemented that I just described. Bidirectional RT star, that's the main comparison here. That is the algorithm that is considered the state-of-the-art implementation of RTs, part of OMPL. And then CHOMP, which is the algorithm that inspired what we're doing here, is in the last column. So we have success rates are reasonably high for the bookshelf for all approaches, but still higher for the approach relying on the sequential convex optimization and doing the continuous time collision checking. Timing-wise, it seems the new approach works fastest, and then path length also gets optimized and is shorter. Then for full body planning, we have a similar pattern where this trajectory optimization tends to work quite well over a wide range of the tests. The reason not applicable for CHOMP is not because the algorithm is not applicable, it's just because the software we had available wasn't applicable to the test cases we had at the time. We've also applied this to higher dimensional motion planning, so 34 degrees of freedom for humanoid, a bin picking task that came from industrial perception task they wanted to do, and also planning with non-holonomic constraints such as needle steering. Now, one direction we're working on a lot right now, where we are also applying this, is beliefs-based planning. And let me give you a little bit of motivation for that first. So the idea here is that a lot of robots that are coming out these days are cheaper than their predecessors, but often it comes at the cost of being a little less precise. In general, we want to use cheap robots, cheap sensors, so we can maybe actually get a robot out there in real-world environments doing things that are worth their cost. But the trade-off you make is that now things are less precise, more uncertainty. And the hope is, of course, that we can maybe somehow compensate for that in software. Just give you a little picture. If you just have a robot going around, there's some uncertainty in its motion, then over time that uncertainty will accumulate if you don't do anything about it. So what do people about it? Well, they might have feedback, so you use a feedback controller, you use sensors that might sense something, and then overall you're able to reduce uncertainty and get something out. What we're interested in here is looking at the POMDP formulation, which is looking at optimizing a plan where the plan is such that you optimize over the sequence of probability distributions that you will encounter. So over time, you'll encounter a sequence of probability distributions. You want to optimize your plan such that that sequence of distributions is good. If you can do that, then you'll automatically veer towards sensors whenever it's necessary to get more information. You'll automatically not worry about that when you already have enough information to achieve your goal. In general, these are hard to solve. So we'll look at a restricted class of problems and a very specific formulation where we can make some progress. So here's a kind of example scenario. Mobile robot starting at the start state is just a dot robot, a point robot, supposed to move to the goal, and there's uncertainty about the initial location of the robot. The disk is giving the 1 sigma uncertainty. If you do state space planning, ignoring uncertainty, this is the path you come up with. It's the best path in state space, shortest path. And you'll have probably even more uncertainty by the time you think you got to the goal and probably are not at the goal. Now, The scenario here is such that when you're in the dark, you don't get to measure anything about where you are. If you're in the light region, you do get to measure something about your position. So a plan we'd prefer would be a plan like this, where you somehow steer towards the light region, localize yourself there, and then come back. You'll accumulate some uncertainty on the way back, but at the end of the day, you have less uncertainty when you arrive near your goal state. The way we are going about it, and some other people have been doing this too, Robert Platt, Jur Vandenberg have been looking at very similar approaches, is to redefine this problem as a planning over Gaussian belief space. So instead of keeping track of the state, we keep track of a mean and a covariance. And we assume that we will run a Kalman filter, in fact an extended or an unscented Kalman filter over time to keep track of the belief state. And we'll try to steer that belief state to a good final state. So now we have a motion planning problem where the dynamics is belief-based dynamics, Kalman filter dynamics. Those dynamics are stochastic because you don't know what you're going to observe, and there might be noise in the dynamics. But whenever you do optimal control in state space, it's a common thing to just determinize the dynamics and replan. So you assume there's no noise on your system, make a plan, execute the beginning of the plan, and replan as you go along. So we'll do the same thing here, just now it happens to be in belief space. So here's what it looks like. You minimize some cost over means, covariance, and maybe the control inputs, subject to the constraints that the Kalman filter dynamics are satisfied, that at the end the mean is equal to the goal, and that the control inputs are feasible. This is the exact same problem we already looked at for trajectory optimization in state space. Just an additional constraint here, but sequential convex optimization can handle those constraints. Now, of course, one tricky part still, which is, well, what happens here? These are local approaches. They'll find a local optimum. If you initialize this with this plan here, you'll be stuck with that plan. You're not going to find the plan that goes into the light region, because locally there is no information telling you that that's where you should go. So the solution there is to use a homotopy method. So rather than using the discrete sensing regions, you use a relaxation of the discrete sensing regions where you assume you have very noisy measurements in regions where you wouldn't get any measurements, but you still get some measurement in those regions. So the shading means now how accurate your measurements are. Completely dark means high noise. The lighter, the less noise. Now you do get enough gradient information. You first solve the problem all the way on the left, which gives you that trajectory. Then you change your problem. You have now a better initialization. Make the noise outside of the sensed region higher. And as you can see, the noise will depend on the distance to the sensing region. And you get a new trajectory. Then you initialize with that trajectory for even higher noise outside of the sensing region and so forth. And finally, you use the original sensing region and get out the optimal plan, in this case, for that original sensing region. You can do the same thing. Let's say you have a robot arm that's occluding an object you're trying to grasp. So you have a 3-link robot arm, a camera sitting here. That's the region it can see. That's the mean initially for the object, but that's actually the true state of the object. It's over there. If you make a state space plan, you execute, you would just get execution like this. Hope to grasp the thing there. Your camera view now covers that part of space, still doesn't see the object, and it doesn't really have a way to adjust to that intrinsically. If you plan in belief space, as you make a plan, you execute your plan, your belief will be updated, you update your plan, and you'll see that you're still not seeing the object, meaning that the object is behind your manipulator arm. You're still occluding it, so you now have a new belief that's centered further out. And as you go along, you then keep replanning and find the object and grab it. Yes? So for these problems, the way we define the problem is that we just require it to reach a goal region, and we define the goal region. So we say this is the goal region. You have to land in that goal region. Then you have success. For state space motion planning, that will then succeed. For belief space planning, if we do numerical evaluations, we will define a region, and then we will make tables. We make tables in which we say how often did you indeed reach that region. one thing I haven't mentioned, but something you also will have to do if you do this in Beliefbased, is you have to still do collision checking. And so what we're doing here is, rather than running an extended Kalman filter, we run an unscented Kalman filter. If you run an unscented Kalman filter, it's convenient to compute sigma points for the locations of all your links. You can compute this convex hull of all the sigma points for each link individually, and then collision check on that convex hull. It turns out that the GJK EP algorithms don't explicitly require that convex hull. If you just give a bunch of shapes and you say collision check for the convex hull of those shapes, they can do it as efficiently as number of shapes times the original cost of collision checking. So this is quite effective to do this. Okay, this gives us the last topic for the talk, the autonomous learning. So here's the problem setup. There's a state space, there's a goal state. There's full state information while your system is executing. You have the ability to send control inputs to the system, but you don't have a dynamics model. And the task is to bring your system to a goal state. The assumption is that even though you don't have a dynamics model, you know there's one that exists. You know that dx dt is some function of x and u, where x is the state, u is the control inputs. But you just don't know f.
Is it deterministic?
In this case, we assume f is deterministic. Correct. But actually, it doesn't have to be, but in all the experiments, we consider it's very close to deterministic. So one way to look at this is a reinforcement learning problem, right? And there's many approaches, and one of the approaches people follow a lot is called model-based reinforcement learning. The idea is you act, build a model based on the data you collected, act again based on that, keep repeating this until you somehow learn enough about the system to achieve your goal. And so that's what we're going after here, and we're doing it in a very specific way. So we run sequential convex optimization with an optimistic version of the current estimate of the dynamics to find a path to the goal state. So for wherever you are in the state space, we do trajectory optimization to find a path to the goal, but we have uncertainty about the dynamics. And the way we encode that uncertainty is by uncertainty ellipsoids, or essentially 3 sigma regions. And we say, within that 3 sigma region, at any given time, you can choose whatever dynamics model that lies within that region. So that's the way we're optimistic. As you design your control, you can choose your dynamics model within the bounds of uncertainty about the dynamics model. Then you execute the first 0.1 seconds of the plan. And then you update the estimates of the dynamics with that new data. Keep repeating this. We use an optimistic model. The consequence is that we are following the kind of standard reinforcement learning paradigm of being optimistic in the face of uncertainty. Often is done through rewards. We're doing it through the dynamics model here. The dynamics model we use, the prior work by Mark Dijsenroth, which does something similar in spirit, uses Gaussian processes. Both this model, the Dirichlet process, Gaussian mixture model, and Gaussian processes can capture a wide variety of dynamical systems models. The reason we switched to this model here is that Gaussian processes get slower as the amount of data grows, because they'll grow cubically with the amount of data in terms of running time, which can become quite expensive. This here will not grow as fast as the best implementations we could find for the Gaussian process models. So here's one example task. Cart pull starts at the bottom. So you can actuate the cart accelerated left, right. The pull is hanging off. It's not actuated directly. So you have 2 degrees of freedom, pull, angle, and cart. You want to swing it up and balance it at the top. Applying the algorithm I showed on the previous slide, here is what happens. So in about 10 seconds, it learned the dynamics model and learned to balance at the top. Doesn't always succeed that fast. There's a little bit of variance there. But over a reasonable number of runs, we have here that after at most 40 seconds, each time it succeeded to swing it up, balance at the top. All right, then just want to conclude. Right now, we're working in my lab on quite a few different things related to robot learning and optimization-based motion planning. Also a bit of work on perception and hierarchical planning that didn't get a chance to talk about, but happy to chat about later. Also want to acknowledge all my collaborators. You can see their initials behind each of the lines of work if you want to match them up. And I want to acknowledge the funding that's behind all these projects. And that's it. Thank you. Questions? Drew seems to have a question.
I have a question. Kind of a philosophical one. You could argue that one of the lessons of machine learning in the last 10 years is that I shouldn't think about, say, learning problems as generic convex optimization problems, right? Because I'll get things that are bad, like cubic scaling and other data points. And I ought to think carefully about the kind of optimization algorithm I run. And usually they end up with something really simple, like integrated descent, quasi-Newton math, or something like that. And I wonder what your thoughts are with respect to throwing something like the optimization problem just into sequential convex optimization. Especially because when I think about what it does underneath, it's underneath the SQP problem, right? Is solving something which looks like, say, either running gradient descent or Newton's method underneath.
Yeah, so I think that's a key. I think that's a really important observation. Is just make sure everybody heard is that even when you run sequential convex optimization, in the inner loop you're solving a convex problem, and solving that convex problem will be done by often a Newton's method underneath, maybe with a barrier, maybe with a primal dual method, depending on what exactly it's doing. And so there's still something going on, and so you might wonder, well, am I not doing double work now because I'm solving these intermediate problems maybe to a too high level of accuracy before moving on, and I'm doing all these Newton steps underneath.
I can think about doing one Newton step, and then I don't even have to think about the sequential quadratic at all.
Exactly. So I think three parts of the answer here to what you're asking. One part is that the really nice thing about the sequential convex optimization in the context of motion planning is that it really nicely accounts for constraints. And so let's say you deal with collisions or boundary constraints. It'll deal with those, and so you might have a pretty big trust region size, whereas your second-order approximation might only be able to handle a smaller region. At the inner loop now, which admittedly has to do a little more work, you have a bigger trust region size, and you are staying away more cleanly from constrained boundaries than you otherwise often would. It's easier to do it this way. Another part of the answer is that if you look carefully at the most advanced methods that do this, some of these most advanced methods need only something like 8 Newton iterations to do this entire thing. So what I presented is kind of the high-level view of kind of intuitively what is going on. But if you look at really advanced implementations like, let's say, in Akado, which is a toolbox out there for these types of problems, you'll see that those implementations actually don't have one mu parameter, as we have in my slide. Those mu parameters are effectively dual variables, Lagrange multipliers. They will simultaneously solve a primal problem and a dual problem. The dual problem will effectively tune individual mu's for each of the constraints in a way that things just work together very effectively, and that they often run in a very small number of total Newton iterations. Of course, if you just run a black box convex optimization solver underneath, you're going to do a lot of Newton iterations overall. And I'd say the third part of the answer is, I think, a difference between machine learning and robotics here, in that in machine learning, it's always more data is better, or should be better. Otherwise, you're kind of doing something wrong, because you should be able to do better with more data. In robotics, it's not always that there is more data. Often, you have a robot maybe 34 dimensions, or maybe in state space 68. But it's not like in machine learning, where all of a sudden you're going to have 1 billion data points, and maybe each of them having thousands of dimensions. So I think the scaling works out a little differently there, in that once you go into the extreme scaling regime, doing one Newton update becomes impractical, and you kind of lose all the benefit you would get from the higher order convergence through each step being very expensive. Whereas in robotics, often the dimensions are lower. And so you can often get higher order methods do better in these problems.
Question.
Yes?
So one of the concerns in robotics is when you get these robots to do things, they do things very slowly, right? Like the video you showed.
Yes.
So do you think the bottleneck is really the mechanical hardware, or is it a bit of you do better with better computers, or it's really the motion planning which is the bottleneck? Which of the three do you think, or is it something else?
If I had to make a guess, speaking for, well, let me just make a statement for my lab, because I can't really say in general what issue would be. But I would say for my lab, probably the bottleneck and why robots move slowly is because there are so many problems to be solved, and it's kind of just more exciting to move on to a new problem. Like once you can, let's say, fold a towel in 2 minutes, it's more exciting to see if you can also master folding a t-shirt or do some tasks with 2 robots folding sheets than to spend that same amount of effort in bringing it down from 2 to 1, whereas maybe it'll come automatically anyway later. So I think a lot of it is motivation of kind of rather moving on to something different than to focus on moving things.
So if you optimize it further, then you think you can make the robots do things at human speed. And so it's really not a
well, I think some work would be necessary. I don't think we can just retime it and it'll do it faster, right? I think some work is needed, but I think often there's so many problems to be solved, and it doesn't end up being any student's favorite problem of all the problems we want to solve, I would say. Yes?
In your non-time problem, you said it will fail usually if there is more than 2 information from the
yes. Mm-hmm.
I think it is mainly due to some kind of extrapolation from your learning configuration. So I just wonder if you have any idea about how we can deal with extrapolation, say using machine learning and machine learning.
Yes, so it is, the learning from demonstrations is definitely doing extrapolation. It's pure extrapolation right now. I think that's one of the angles where if it were combined with, let's say, some ideas from the Gaussian mixture modeling approaches, it might give a way to interpolate between multiple demonstrations in a nice way. It might just be the case that with enough demonstrations and not requiring to extrapolate too far, it might just work. So one thing we're looking at right now is, if you look at the learning from demonstrations literature, a lot of it has maybe 5 or 10 or maybe 20, 30 demonstrations. What if we can put in the effort to collect 10,000 demonstrations, right? What's the range of generalization, so to say, but it's not really generalization, it's just kind of more covering the space. How densely do you need to really cover the space to get out performance that's good enough for a wide range of initial conditions? And so what we're doing for that is, right now we're looking at, we 3D printed equivalents of the PR2's grippers to limit the human dexterity in the demonstrations, and we're looking at setting something up, we don't know exactly what yet, that would track humans while they're demonstrating to make sure that maybe they don't exceed the workspace constraints of the PR2. So you're really buzzed every time in some way that when you're exceeding it, so you get feedback and learn how to stay within the constraints and give demonstrations that are useful. Maybe 30 seconds per demonstration. I think in about 2 weeks, full-time demonstrating, we should be able to get to 10,000. Sid. Oh.
We're clapping. I'll ask you a question anyway. When I think of non-tying, you talk about these deformations from one configuration to another, but oftentimes I think of it as critical events. You want this loop to go on top of something, and some other thing to go under something else. And I wonder if this sort of coming up with a deformation misses out on the fact that it's not as important getting the matching right, but getting these critical events right, because the rope could be on top, it could have a lot of slack on where it could be on top. Do you have some thoughts on how you may incorporate these critical events into your maps?
So first, certainly, I think you could get much wider generalization if the system understood the topological aspects rather than just the geometry. Right now, we don't have a really good handle on how we would do this. We have some ideas that we might want to try. So one idea is if you look up in multiple demonstrations, you might have features. When you compute your distance metrics, you would have features that relate to topology more directly rather than geometry. And maybe then if you grab a demonstration, you would grab one that topologically is more closely matched with your current situation, even if geometrically some things might be quite different. So that would be one angle. Another related angle is that, in fact, in general, the closely matched geometries don't need to be the best demonstrations to use, because it's possible somebody gave a very non-robust demonstration. Gripper barely open enough to grasp something, but the scene was perfectly matched. That might not be a good demonstration to grab. So in general, it seems there's a lot of other information that we need to somehow collect from the demonstrations about how robust things are, related to either topology or variation in execution, slight variation, what the effect will be in terms of robustness. But we don't have a good handle on just plugging something in and getting something to work.
I suggest we thank the speaker, and then he's going to be around to post some of the reception.